Hello and welcome back to another multivariable calculus 3 video. Today we will be talking about linear approximation, something I briefly talked about in the last video. While discussing tangent planes, you'll understand why I talked about it and why they are kind of related with each other. To use the simplest words, why they're kind of related to each other. Well, we're going to be asking the big three today: what, why, and how. The what, well, what is the linear approximation? Well, we're going to be looking at all three of their calculuses today. Going back to Calc 1, well, we're essentially approximating a function at a point x is equal to a. So what that would look like is our linear approximation of x is equal to f prime of x times x minus a plus f of a. Pretty simple, perhaps difficult back in the day. Now it's just kind of something that's fundamental. So our L of x approximates our f of x at some point near a. So this could be a plus zero point 0.1 or a plus 0.01. It's going to approximate it pretty darn well, or well enough for the purposes that we need, I guess. Looking at a calculus 2 perspective, well, what were we doing calculus 2? What we were doing is Taylor series approximation. Well, what is our Taylor series? I believe I wrote it right here. If I did, and I apologize. But that's essentially what our Taylor series approximation is. And if I remember correctly, what is our Taylor series approximation for our linear? It should just be our f prime of x times x minus a plus our f of a, and maybe one more before this. I actually do not recall. I apologize. X minus a squared. Okay, I think that was our linear approximation using our Taylor series. Regardless, we approximated using Taylor series in Calculus 2. Now, looking at the Calculus 3 picture, well, I'm not going to spoil it quite yet, but what are we doing? Essentially, what we're doing is we're approximating a function at some point a, b. Now, we're doing it in multivariable, where in our linear approximation roughly equals our function. So what's the big picture here, I guess, is the question. Well, the big picture is no matter what calculus you do it in, linear approximation is going to give you a pretty darn good approximate at some point near wherever you're taking your linear approximation function of. So the y, although it seems redundant, linear approximation, why are we doing it? Well, we're doing it to approximate. Perhaps this was useless to include, but I just got to make it clear that we're approximating using linear approximation in all three of the calculuses, just in multivariable for Calc 3. So I guess the how now, well, there's two different ones that we're doing, two different functions and like kind of theorems, maybe if you will, that we're going to be using here. So our linear approximation of xy at some point ab, well, let's go at ab here. Well, this is just going to be our f sub x at that ab times our x minus a plus our f sub y. Remember, these are partials at ab times x, or y minus b, apologize, plus f of ab. Well, just out of curiosity, what does this look like? Well, what this looks like is our explicit function, tangent plane, all right? So I guess maybe I overlooked it in the last video when talking about tangent planes, but with tangent planes, I like to do implicit, but when I'm asked to approximate, this is what we're going to be using here. So our L of xyz, well, it's just going to be the exact same thing here. Ooh, actually, you know what I can do is I can just copy and paste. Nah, there's a C now, huh? Can't really do that. Whatever, we'll write it down. Partial of x at ABC times x minus a plus our partial of y at ABC times y minus b plus our partial of z at ABC times y minus c plus our f of ABC. That is essentially how we're going to be doing it at some point AB. I guess there's nothing really else to explain other than let's just go ahead and dive right into an example. Definitely going to be beneficial here. We're going to find the linear approximation of f of xy is equal to x squared minus xy plus 1/2 y squared plus 3 at the point 3, 2. And then we are going to approximate f of 3.1, 1.9. Get your calculators out. I'll spoil it. We're going to go ahead and see how close we are, I think. I'm thinking is what we're going to do. So, well, what's our linear approximation formula for xy? Well, let's go up here and then just duplicate this. Comment. Bring it down. Well, let's do it. Well, let's go ahead and find our two partials at this point A, B, or 3, 2. Well, let's go ahead and do that. Our partial of x is going to equal, what is it going to be equal to? 2x minus y, I believe. At the point 3, 2, this is just going to be equal 6 minus 2, 4. F sub y, take the partial of y, x squared 0 minus xy, that's going to be negative x plus power rule plus y, so we have negative x plus y at the point 3, 2. That's going to equal what? Negative 3 plus 2 is going to equal negative 1. Okay, well, those are 2 points that we really needed there. Well, what is our f of AB? F of AB, which is going to equal f of 3, 2. Well, what is 3, 2? We got 3 squared, 9 minus 6 plus 1/2 times 4, 2 plus 3. So that's what? 5 plus 9. That's 14 minus 6. That's going to be 8. Sorry if I did that in my head. It's just simple algebra. You can go ahead and prove it if you really wanted to. Go ahead and take my word for it, I guess. Or maybe don't. Be skeptical. Go ahead and prove it. That'd be great. Maybe good practice algebraically. Make sure you don't make a simple mistake on an exam in the future. So now we have all of our components, really. So what is our f of xy, or our linear approximation at 3, 2? Well, it's going to be f sub x. That's going to be 4 times our x minus, what is our point 3? X minus 3 plus our f sub y. That's going to be negative 1. So we're just going to do a negative 1 times y minus 2 plus our f of AB, which is going to be 8. That's going to equal our linear approximation at, well, I guess it would be, we'll keep it xy. Yeah, we'll keep it xy. I was almost hesitant to do that because this is the linear approximation at the point AB, but we'll just keep it xy. So algebraically, the question is, do we want to simplify this? The answer is no. We could make our job more difficult. Well, so yeah, that's a short answer. It's going to make our job more difficult, and perhaps you can see that when we're asked to approximate the function at 3.1, 1.9. This is going to be a pain in the butt, essentially, to approximate if we wanted to do that, because then we'd have 4 times 0.4 minus 12. It's just not worth it. So we're going to go ahead and simplify this just a little bit. Perhaps redundant that I was just making a big old spiel about not doing it, but we just got rid of the negative 1, essentially. So that's our linear approximation at xy. Well, we found our linear approximation at the point 3, 2. Well, that's step 1. So now we're asked to estimate f 3.1, 1.9. Well, let's go ahead and do that. So L of xy, so that's going to be our linear approximation at 3.1, 1.9, which is going to equal 4 times 3.1 minus 3 minus, what is this, 1.9 minus 2 plus 8. So this is our linear approximation here. So let's see this, actually. Go ahead and pull out your calculator and let's see. Can we do this? Um, this is why I was advising to have a calculator perhaps during this one. Oh man, my battery's low on this one. Let's make this fast. 4 times 3.1 minus 3 minus 1.9 minus 2 plus 8. I got 8.5. So our linear approximation is 8.5. Well, let's go ahead and see what our function actually is at our 0.19. So what is this? Ooh, going to be a little bit ugly to do, but we're going to do it. So we got 3.1 squared minus 3.1 times 1.9 plus 1/2 times 1.9 squared plus 3. Assuming I did my calculating right, I got 8.525. As you can see, pretty darn good approximation given that, you know, what if we had some kind of, I guess this applies more to Taylor series than anything, so maybe I'm not going to go into that. But this is a pretty darn good approximation. So what are we, 0.025 off? I mean, we're in the hundredths off from our actual. So I guess that's exactly what linear approximation in Calculus 3 is. I guess there's really nothing more to say about that. It's pretty nice to be able to approximate three-dimensional or multivariable functions here. As you can see, our linear approximation will do just fine to the 100th error. Something you may have observed in Calculus 1 and 2, or perhaps not. Maybe you had different experiences in Calc 1 and 2. But for Calc 3, our linear approximation is going to work just fine. We can perhaps see why this was tied to our tangent plane, because realistically what it is it's just implicitly or explicitly defined. So yeah, that is our linear approximation in Calculus 3.